net's build costs are the vehicles, the network elements, and the energy system. Although vehicles are the biggest single CUTS capital cost, for LAN and WAN, they are insignificant relative to the other two costs. Relative to all CUTS roads and rail nodes, LAN and WAN requires 10 times fewer vehicles. Each vehicle requires far less than 10% as many resources to build, and each vehicle would have 10 times the average vehicle lifetime range. The total cost for LAN and WAN vehicles is then 1,000 to 10,000 times smaller than the CUTS road and rail vehicles. NetSair would initially use a small subset of the existing CUTS airplane fleet. There would be no new capital cost for airplanes. However, the CUTS plane should be modified to increase comfort for all passengers, decrease boarding times, and if required, ensure use of renewable biofuels. Land passenger vehicles are mainly just motorized and automated versions of today's small personal vehicles, like recumbent trikes, scooters, skateboards, and wheelchairs. The other vehicles are split between propulsion and control units, and trailers that support either pairs of passengers or various sizes of NETS boxes. The box-carrying trailers also have the small and simple robot arms that push boxes off the trailers or pull them on. Motor sizes are less than 1 kilowatt. These clearly take far less than 10% of the resources of even the smallest CUTS car. WAN vehicles have 3 module types, with all sharing 1 or 2 bogies depending on type. All these elements are small, lightweight, and mechanically simple, requiring minimal resources. The bogies provide the track-to-vehicle module interfaces. Structurally, the bogies are similar to pairs of rollerblade wheels assemblies joined together with a carbon fiber rod-based assembly. The assembly protrudes in the front and back, with male and female dynamic coupling devices at either end. The center of the assembly supports a pole descending through the opening in the track. A balancing mechanism is used to handle any lateral forces the pole experiences, such as at switches or on turns. The cars mostly consist of 2 fiber composite shell elements. The floor element that descends to perform the loading and unloading, a slightly oblate aerodynamic bullet-like cylinder with a gap in the bottom into which the floor fits. The total area of the 2 shell parts is under 30 square meters, with a total mass less than 30 kilograms. The surface of the shell interiors would be covered in a flexible organic LED to allow passengers to have a view of the vehicle surroundings if they want, or any other things they would like displayed. This provides a useful alternative to windows. At high speeds, windows would create comfort issues for some. The components that lower and raise the platform consist mostly of a small motor with 4 small cables inside lightweight telescoping poles. A couple of simple structures would also be used to make the descents and ascents safe. The taxi passenger configurations use chairs resembling high-quality reclining mesh deck or office chairs with carbon fiber frames and embedded thermoelectric heating and cooling elements. These would have masses below 10 kilograms. As with the other 2 cargo configurations, the assembly holding the chairs would be locked into place on the car floor. The NETS box carrying configurations provide a carbon fiber rod-based shelf structure into which the boxes can be placed or removed by land goods robot arms. The propulsion modules would largely consist of a bogie carrying a small battery pack with electric motors of various sizes turning a propulsion wheel or wheels. The battery modules are primarily just bogies with a large battery pack hanging at the end of the bogie pole. The WAN vehicles clearly then use a small amount of materials and can be manufactured and maintained very easily. The average CUTS personal vehicle mass is over 1,600 kilograms, with commercial vehicles being much heavier, although there are far fewer of them. All have a large number of moving parts and a high manufacturing complexity. The ratio of 10 to 1 in resource requirements per CUTS vehicle versus WAN or LAN vehicles is very conservative. WAN vehicles have high duty cycles and reasonably high average speeds, indicating a capability to provide well over 500,000 useful vehicle kilometers per year per vehicle. The covers and elevation limit most weather effects. With aggressive preventive maintenance of all modules, vehicle lifetime should be capable of far more than 5 million trip kilometers. The average CUTS personal vehicle in the US has a lifetime range of about 300,000 kilometers. CUTS commercial vehicles have much longer lifetimes than personal vehicles. However, that decrease in the WAN lifetime advantage is offset by the even greater resource requirements per vehicle. The net result would be that a claim of a 10 to 1 advantage in lifetime trip kilometers for WAN vehicles relative to CUTS vehicles is again quite conservative. The number of cuts road vehicles is usually expressed as a count per 1,000 people. This chart gives those rates for the countries with more than 20 million vehicles. Many of these countries have rates above 600 per 1,000. Another 25 countries have such rates. That is also the case in the more developed areas of countries with lower rates, with most areas heading there as they develop. The vast majority of those are personal vehicles used primarily as people movers, with goods carrying use limited to purposes like shopping. Land, passenger, and goods vehicle rates would be less than 10. WAN intercity vehicle rates would be less than 20, with the regular WAN vehicle rate at less than 40 per 1,000 people. The low LAN and WAN vehicle counts are largely a result of the temporal sharing model, combined with low trip lag times, enabling each vehicle to perform many more trips per hour than CUTS vehicles. To understand how this gives rise to the low LAN and WAN vehicle counts, consider this chart of U.S. household CUTS vehicle trips in 2022. There were about 3 trips per day in 2022. In 2017, the number was a bit over 5. The reductions come from more people working from home and internet effects on the demand for shopping and personal errand trips. There is no reason to believe that these trends toward reduced trip demand would reverse. It seems far more likely that trip demand, and particularly peak demands related to work commutes, would continue to decrease. The question is then, how does peak demand vary with respect to averages reflecting hourly rates of less than 0.3 trips per person per hour? Peak trip demand comes during rush hours. That demand is primarily for work or school commutes. About 400 trips per 1,000 involve CUTS vehicles for those commutes. If we assume 2-hour-long rush hours, there would be less than 200 trips per hour. Peak demand would be higher than the average, but this would be offset by factors like the fraction of the commutes done outside of rush hours. As shown earlier, land vehicle trips, from the time they start to respond to a passenger trip request to when they are available for the next trip, at least in settlements, should average less than 90 seconds. That means each land vehicle would support 40 trips per hour. Each passenger trip may use 0 to 2 land legs. This indicates 10 land passenger vehicles would be sufficient to support peak demand. For WAN, the trip length is a factor. From the chart, the average U.S. commute trip is about 20 kilometers. The average WAN passenger carrying vehicle would then support about 7 trips per hour, including loading and unloading times and repositioning after drop-off. That would indicate about 30 vehicles to support 200 trips per hour. Less than 5 more per 1,000 would be required to satisfy the response time constraint. The same WAN vehicles are used for goods movements, which are largely replacing the short-haul commercial vehicle movements. Few freight trips need to be performed in peak passenger demand hours. We compute the freight vehicle demand based on current demand for CUTS ton kilometers and an average goods load of 150 kilograms, with an average freight vehicle speed of 100 kilometers per hour. That gives a demand of about 22 freight vehicles per 1,000 people. Using a similar type of analysis for intercity WAN vehicles gives a freight demand of less than 20 vehicles per 1,000, with passenger demand at less than 1. This is largely due to the high speed of the intercity vehicles, including the freight ones in long trains. Note that about 50% of the freight demand uses rail. The majority of that is carrying coal and a few other bulk goods along mostly remote tracks. Just leaving the coal to rail would reduce the WAN vehicle count by 16%. Also, as with coal, there are strong reasons, some described soon, to believe that if nets were adopted, the demand for long-haul freight shipments would decline significantly. In summary, we have shown that a trip demand, like that in the US today, could be satisfied with a WAN and LAN vehicle fleet, with amortized capital costs in the range of 5 thousandths to 5 hundredths of a cent per passenger kilometer or goods ton kilometer.